Welcome to the debate. So, when you pour the foundation for a skyscraper, there is this incredibly narrow window of time where the concrete is wet.
Right.
You can shape it, smooth it out, set the rebar. But once that concrete cures, it is set. If there's a structural flaw or a crack, you are basically building the entire rest of that massive structure on compromised footing.
Yeah, and it's a terrifying thought when you apply that to human biology.
Exactly. What if human biology works the exact same way? What if the specific microbes colonizing your gut during your first 1,000 days of life permanently hardwire your risk for obesity or asthma and Alzheimer's? And this is the key part. What if nothing you do as an adult can truly rewrite that foundation?
Well, I look at it from a completely different angle. Biological systems aren't rigid, concrete skyscrapers. The human body, and specifically the microbiome, is much more like a bustling living city.
A city?
Yeah, sure, the original roads might be laid down early, but you can always reroute traffic, you can demolish old buildings, adapt to the current population. The weather changes, the demographics change, and the city continuously adapts to survive.
And that fundamental tension is exactly what we are unpacking today. We are looking at one of the most consequential questions in modern human biology. Are our immune and metabolic health trajectories strictly determined by our early life microbial exposures, or does the adult microbiome remain so fundamentally plastic that real-time environmental factors can continuously override that early developmental programming?
It's a massive question, really, and it has profound implications for how we treat disease. So we'll be drawing on a really rich body of recent source material today, everything from comprehensive epidemiological meta-analyses and highly controlled gnatobiotic mouse models.
The germ-free mice.
Right, the germ-free mice, all the way to massive longitudinal human cohort studies that have tracked exactly what happens during this critical window of opportunity in microbiome development.
Well, I'll be representing the early life determinism perspective. My position is that the infant colonization process is not just, a casual gathering of bacteria. It establishes an unalterable immunological architecture.
The permanent hardware.
Exactly. I'll argue that disruptions to the neonatal microbiome create permanent immunological scars that dictate lifelong health. And once that developmental window closes, the baseline hardware of the immune system is set for life.
And I will be taking the lifelong plasticity perspective. I argue that the adult microbiome operates as a highly dynamic, really resilient ecosystem.
But resilient enough to overwrite infancy?
Yes, absolutely. While early life obviously provides a starting point, the sheer ecological pressure of our adult diet, our lifestyle, and targeted metabolic interventions can essentially overwrite, or at the very least continuously compensate for those early life signatures.
Let me lay out my position in a bit more detail, because I think the severity of this gets overlooked. Infancy is a completely non-redundant, absolutely critical developmental window.
Non-redundant meaning you can't just fix it later.
Right. The early microbial colonizers are not just passing through the infant gut as passive passengers taking up space. They are epigenetic engineers.
Disruptions during this time, whether a baby is delivered via cesarean section or exposed to early and aggressive antibiotics or, deprived of the complex sugars in breast milk, these create irreversible structural deficits in how the immune system learns tolerance.
Irreversible is a very strong word.
But it literally changes how the neuroimmune system matures. We call this an immunological scar. It dictates a lifelong susceptibility to conditions like asthma, atopy, and systemic metabolic disease. You can change your diet at age 30, sure, but you are running that new diet on permanently compromised hardware.
Look, I hear the logic there, but I think it dramatically underestimates the sheer biological plasticity and the functional redundancy of the human superorganism. How so?
Well, the gut is not a museum preserving the history of your infancy. It is an active ecosystem, subjected to massive daily ecological pressure. We are talking about the continuous impact of adult diet, stress, medications, and targeted lifestyle interventions.
But those are just surface-level changes.
I wouldn't call them surface level. These forces can substantially remodel both the physical structure of the microbiome and the chemical metabolites it produces. A transient early life disruption does not biologically doom a host.
Doom might be a bit dramatic, but it sets the ceiling.
I disagree. The ongoing real-time software of the adult microbiome is constantly running updates, and those updates can continuously compensate for any theoretical flaws in the original hardware.
Let's actually dig into the mechanisms of how our immune system develops then. Because when you look at the molecular level, it's very clearly not just a simple software update. To understand this, we have to look at not-abiotic models.
Ah, the sterile bubbles.
Yes, germ-free mice raised in completely sterile plastic isolator bubbles. They've never been exposed to a single microbe. When we study them, we see strict determinism at play. Without early microbes, these animals literally fail to develop proper gut-associated lymphoid tissues.
Sure.
But the most striking mechanism is what happens to a very specific type of cell called an iNKT cell, or invariant natural killer T cell.
Right, and for context, these are the unconventional immune cells that act essentially as the riot police at mucosal surfaces, like the gut lining and the lungs.
Exactly. They're the riot police. Now, in a healthy state, commensal microbes send chemical signals that calm these cells down, keeping their numbers low. But in germ-free mice, these highly inflammatory cells hyperaccumulate. They just swarm the gut and the lungs.
Because they don't have the microbes telling them to stand down.
Right. And we now know the exact mechanistic reason why. The absence of early microbial signals causes hypermethylation at a specific genetic locus. It's the CXCL16 gene.
Let's break down what hypermethylation actually does in this context, because that's where the rubber meets the road.
Yeah, think of it like a biological thermostat. Hypermethylation essentially jams the genetic switch in the on position. Because those early microbes weren't there to calibrate it, the body permanently overexpresses the CXCL16 chemokine, which is this distress signal that constantly recruits these inflammatory cells into the tissue.
So the thermostat is stuck.
The thermostat is permanently set to 90 degrees, yeah. So the tissue is always running hot with inflammation. And here is the devastating part for the plasticity argument. If you take these germ-free mice out of the bubble and introduce a perfectly healthy microbiome in adulthood, it completely fails.
Fails to do what exactly?
It does not fix the hypermethylation. It does not reduce the disease susceptibility. The developmental window is closed, the thermostat is broken, and the inflammatory scar is permanent.
I understand the mechanism, I really do, but I seriously question translating a germ-free mouse perfectly to human health. It is an extreme biological artificiality. Humans are never entirely germ-free.
Well, even in humans.
Wait, hear me out. Even a baby born via C-section in a sterile operating room is colonized immediately. It's just colonized by a different profile of microbes, typically skin flora and hospital environmental bacteria. If early life immune programming builds the structural walls of your house, your adult lifestyle is the daily weather beating against it.
The weather can't fix a broken wall, though.
But a perfectly built wall can still erode under a continuous storm, and a flawed wall can absolutely be reinforced and patched. Just look at the extreme short-term plasticity of the adult microbiome. If a human switches to a high-fat, heavily meat-based diet, we see massive blooms of bile-tolerant bacteria like Bilophila wadsworthia within a mere 24 to 120 hours.
Yes, the populations shift rapidly.
That isn't just a slow shift. That is immediate, sweeping ecosystem remodeling.
I don't dispute that the ecosystem shifts, but you're conflating a temporary operational shift with structural architecture. Yes, the Bilophila blooms, but the baseline immune tolerance of the gut wall doesn't fundamentally rewrite itself. Let's look at another specific immune cell, mate cells.
Mucosal-associated invariant T cells.
Right. They rely strictly on early life exposure to riboflavin derivatives. Certain gut bacteria synthesize this vitamin B2 byproduct. If a neonate is given broad-spectrum antibiotics, it wipes out those specific riboflavin synthesizing bacteria.
Okay, temporarily wipes them out.
Temporarily wipes out the bacteria, yes. But because the infant lacks that chemical signal during a crucial developmental window, the physical abundance of mate cells in their lungs is permanently stunted.
Interesting.
Later in life, even when the antibiotics stop and the gut bacteria fully regrow, Those adult mice remain highly susceptible to bacterial pneumonia. Regrowing the bacteria in adulthood doesn't spontaneously generate the immune cells that failed to develop in infancy.
Sure, but the host doesn't exist in a vacuum. Even if the absolute count of MAI T cells is lower, the adult host can upregulate entirely different immune pathways to compensate.
Upregulate what exactly?
Well, if you give that adult host the right dietary substrates, like fermentable plant fibers for instance, their newly remodeled microbiome will produce large amounts of short-chain fatty acids, which actively suppress lung inflammation. You don't need a perfect blueprint if you have functional redundancy stepping in to patch the leaks.
But let's step out of the laboratory cages for a second. If you're a parent listening to this, you might be thinking, does this invisible scarring actually happen to human children in the real world? And that is the big question. And the answer is unequivocally yes. We don't have to rely solely on mouse mechanisms. We have longitudinal human epidemiological data. The child cohort study provides undeniable proof of this exact window of opportunity. Researchers rigorously tracked the microbiomes of children from birth and found something remarkable. They identified 4 specific keystone bacterial genera: Faecalbacterium, Lachnospira, Veillena, and Rothia. We call them the FLVR bacteria.
Right, the FLVR group.
If a child experiences a depletion of those 4 specific bacteria during their first 100 days of life, it highly predicts clinical asthma by age 3.
But come on, infant microbiomes are notoriously chaotic. Microbial populations fluctuate wildly week to week.
And that chaotic fluctuation actually proves the determinism argument.
How?
Because the child study found that by the time these children reach 1 year of age, those FLVR bacteria had often naturally returned to normal levels.
Okay.
But the children still developed asthma at age 3. The physical presence of the bacteria later on didn't save them. The crucial calibration of the regulatory T cells was missed during the first 100 days. The bacteria eventually showed up to the construction site, but the foundation had already dried. We see the exact same thing in the washout phenomenon documented by the Wellcome Sanger Institute's Baby Biome study.
Ah, you're talking about the study showing that the differences between C-section and vaginal microbiomes eventually disappear?
Precisely. If you look at a C-section infant and a vaginally delivered infant at birth, their microbiomes are radically different. But by exactly 1 year of age, those massive taxonomic disparities wash out. If you look at their sequencing data at 12 months, they are completely macroscopically indistinguishable.
They look the same.
They look identical, yet despite having the exact same microbiome at age 1, the C-section children retain significantly higher long-term risks for childhood obesity and asthma. Why? Because the pioneering microbes already did their job. They set the epigenetic legacy in those first few months, and then they vanished. The foundation was already poured.
That is a very powerful narrative. But the epidemiology surrounding C-sections is incredibly noisy, and we have to be very careful about assigning causality purely to the birth canal microbes.
The correlations are very strong, though.
Strong correlations don't eliminate massive confounding variables. Mothers undergoing surgical deliveries are almost universally administered intravenous intrapartum antibiotics, which cross the placenta. Furthermore, C-sections involve major abdominal surgery, which frequently delays lactogenesis, meaning those babies often experience delayed exclusive breastfeeding.
Which affects the microbiome.
Exactly. So we have to ask, are we measuring the biological absence of vaginal microbes, or are we simply measuring the collateral damage of heavy antibiotics and the lack of complex human milk oligosaccharides in those early days?
Well, even when researchers statistically control for breastfeeding duration and antibiotic use, the metabolic and immunological risks remain elevated for surgical births.
But we also have to look at the sheer math of the human lifespan. If you are telling me that a 100-day window is the primary deterministic driver of a metabolic disease that manifests when someone is 40 years old, how do you mathematically isolate that from 4 decades of eating ultra-processed diets, enduring chronic psychological stress, and exposure to environmental toxins?
Because the baseline was set early.
But look at the human migration studies demonstrating rapid microbiome westernization. When individuals migrate from non-industrialized nations to highly industrialized ones, they rapidly lose their native microbiome diversity. Within a very short period, they adopt the exact metabolic disease risks of their new environment, completely independent of how they were born or what their first 100 days looked like. Their adult environment violently and effectively reshaped their microbial communities, overriding their birth story entirely.
I completely agree that the adult diet matters immensely. Nobody is arguing that eating ultra-processed food for 40 years won't make you sick.
Glad we agree on that.
But my point is about the baseline. If your baseline threshold for inflammation was set artificially low during infancy because of a disrupted microbiome, that adult environment is going to trigger disease much faster and much more severely. And that brings us to a really practical, urgent question. If this determinism is real, how do we actually treat it?
Interventions.
Yes, because if the window closes, early ecological matching isn't just a nice idea, it is paramount. We cannot just throw adult solutions at developmental problems. Look at the clinical failure of vaginal seeding.
Right? Vaginal seeding was a massive trend for a while. This is the practice of literally swabbing a newborn C-section baby with maternal vaginal fluids immediately after birth to simulate passing through the birth canal.
Exactly. It made intuitive sense, but when we finally ran robust randomized clinical trials, it yielded absolutely no significant differences in BMI or allergy risks by 24 months. It failed, and the biological reason why it failed is fascinating.
Because the flora was wrong?
Exactly. The pioneering flora of a healthy infant doesn't actually come from the vagina at all. During natural labor, the baby is colonized by the maternal gastrointestinal tract via natural fecal contamination. Vaginal seeding fails because the adult vaginal microbiome is relatively simple and heavily dominated by lactobacillus. It's an ecological mismatch for an infant gut that needs complex fermentative bacteria. It literally seeds the wrong biome.
I will readily agree that vaginal seeding was ecologically naive. It was an oversimplification of a complex transfer process.
But contrast that clinical failure with the landmark University of Helsinki study. They didn't use vaginal fluids, they used highly targeted postnatal maternal fecal microbiota transplantation, or FMT. They took a tiny 7 milligram dose of highly screened maternal feces, dissolved it in breast milk, and gave it to C-section infants immediately postpartum.
7 milligrams is incredibly small.
The precision here is incredible, and the results were transformative. That tiny, precise ecological match rapidly restored normal bacteroids transmission and completely corrected the inflammatory trajectory of those C-section infants before the developmental window closed. It proves that to fix the foundation, you have to hit the exact right timing with the exact right ecological consortium.
I will absolutely acknowledge the elegance of that Helsinki study. It is brilliant, incredibly precise science. But proving that early intervention works does not preclude the fact that the metabolic software can be upgraded in late life to rescue the host.
Upgraded to what extent, though?
Well, you don't have to have a time machine to fix a broken immune system. Let's talk about aging and cognitive decline, which I'd argue is the ultimate test of long-term health and plasticity. Researchers at Stanford Medicine and the Arc Institute conducted a groundbreaking study on aging mice that completely validates the power of late-life intervention.
Ah, you're referring to the pathways connecting the aging gut microbiome directly to memory loss in the brain?
Yes, they set out to solve a mystery. Why were these aging mice losing their cognitive function? The culprit wasn't in their brains, it was in their gut. As the host ages, specific microbes, notably one called Parabacteroides goldstanii, begin to proliferate abnormally.
And those are metabolically active, right?
Highly active. These bacteria are metabolically hyperactive. They overproduce medium-chain fatty acids, or MCFAs. These MCFAs don't just stay in the gut. They accumulate in the intestinal tissue and trigger local immune cells to release massive amounts of a pro-inflammatory cytokine called interleukin-1 beta.
Which then signals the brain.
Right. This inflammation literally travels up and blocks the sensory neurons of the vagus nerve, which is the biological superhighway connecting the gut to the brain. By blocking that nerve, it severs communication to the hippocampus, driving severe cognitive decline.
And your argument is that this entire cascade isn't hardwired by early life?
Exactly. It is a real-time, continuous, metabolite-driven phenomenon. The mice weren't doomed by their infancy. When the Stanford researchers intervened in these elderly mice using highly targeted bacteriophages to kill off the specific bacteria, or shifting them to diets like ketogenic or Mediterranean protocols to boost protective short-chain fatty acids, the results were stunning.
They reverse the cognitive decline?
Yes. The targeted intervention lowered the MCFAs, the neuroinflammation receded, the vagus nerve unblocked, and cognitive function was actively rescued in old age. It proves that you do not need to alter the permanent hardware baseline of infancy if you can actively manipulate the real-time metabolic software. If you can use diet or therapeutics to keep systemic inflammation below the disease threshold, the early life blueprint simply doesn't dictate your destiny.
I see the power of that mechanism, I really do. The gut-brain axis is incredibly dynamic. But let's look at what we've synthesized here today regarding the entire lifespan. My position remains that while late-life rescue is possible in specific pathways, the first 1,000 days undeniably set the absolute immunological ceiling of the host.
The ceiling, sure.
Early developmental scars, whether we are talking about the permanent hypermethylation of the CXL16 genetic locus or the physical pruning of the immune system due to neonatal antibiotics, they just cannot be entirely unwritten. While adult lifestyle matters deeply, the foundational hardware is permanent, and it dictates how hard you have to work as an adult just to stay healthy.
And my summary is that the microbiome possesses an immense, almost unfathomable ecological resilience. The adult gut isn't a static museum of your infant history. By actively manipulating real-time microbial metabolites, our daily software, we have a continuous, lifelong compensatory mechanism.
Even against structural deficits?
Yes. This plasticity is so powerful that it is fundamentally capable of overriding the physiological trajectory of aging and disease, regardless of how you were born or what you were fed in your first year.
I think where we fundamentally converge today is on the complex beauty of this dual reality. Early life microbial exposures undeniably draft the host's biological blueprint. They pour the foundation and establish the absolute boundaries of immune tolerance.
But continuous, lifelong environmental and dietary interventions dictate how efficiently the human organism operates within those boundaries. The hardware might give you a baseline limit, but the software dictates your daily physiological performance.
Precisely. Navigating this dual reality of early determinism and lifelong plasticity reveals just how brilliantly complex human biology really is. But more importantly, it provides multiple therapeutic avenues for us to explore in the material. We aren't limited to just one solution.
Right, it's not hopeless.
Exactly. We can focus on optimizing maternal health and precisely managing the first 1,000 days, while simultaneously developing precision diets and phage therapies for our senior years. We leave it to you, the listener, to weigh this evidence and determine the ultimate balance of power between your microbial history and your present choices.
It really comes back to where we started with your opening analogy.
It does. You might not be able to change the fact that the concrete foundation of your building has a slight tilt to it, but if you are an expert architect, equipped with the right tools, you can absolutely engineer the rest of the skyscraper to stand tall, weather the fiercest storms, and thrive in the city.
Beautifully said.